In this lecture, I will start by reminding you about the channel capacity in the case when you transmit from one antenna to another antenna. And then we will extend this to the case when you have multiple antennas at either the transmitter or at the receiver, and we will see what the capacity becomes in that case. Then we will look at channel modeling for that particular case, in particular when you have line-of-sight channels. So the transmitter and the receiver sees each other and there's no other objects around. And then based on that channel model, we will also look at the structure of transmitted signal. How does it look like? Is there a beam that is being formed? In this and a number of following lectures, we will concentrate on point-to-point channels, where you have one transmitting device and one receiving device. And you can create taxonomy of different point-to-point channel depending on how many antennas you're having at the different devices. In the point-to-point SISO channel, standing for single input, single output, you have one antenna at transmitter and one at the receiver. In the point-to-point SIMO channel, which stands for single input, multiple output, you have multiple antennas but only at the receiver side. At the point-to-point MISO channel, which stands for multiple input, single output, you have multiple antennas at transmitter. And finally, at the point-to-point MIMO channel, which stands for multiple input, multiple output, you have multiple antennas at both the transmitter and at the receiver. In this lecture, I will start with a recap of the capacity of the SISO channel, and then we will extend it to the SIMO and the MISO channel cases. And we will leave the point-to-point MIMO channel for a later lecture. In wireless communication, the transmitted power is diffusing when it leaves the transmit antenna, and that means that not all transmit power is being received. If you have an isotropic antenna that spreads out the signal energy equal in all directions, well then at a distance d, if you have an isotropic receive antenna as well, then this is the fraction that you are receiving at distance d and when you have a wavelength lambda. And typically, in wireless communications for mobile applications, so you have like 50 up to several kilometers of distances, well, you're losing say 70 or up to 130 or 140 decibels. So that means that when we are looking at the point-to-point channel, in the memoryless case like this, where you transmit the signal and it goes over a channel that multiplies with a channel response G, and then you received the signal Y here with noise in it, then the absolute value square of G is typically between minus 70 decibel and minus 130 decibels. Sometimes people are writing the path loss with a minus sign in front of it, and sometimes they omit that sign. However, it's always easy to see which is the case, because you can never get more power at the receiver than you actually transmitted. The capacity of a memoryless SISO channel is discussed in detail in a background video. Now I will just describe that you have a system model in the symbol sample complex-baseband, where you are transmitting symbols, discrete symbols with L being a time index. They always multiply with the channel response, and you receive a signal YL plus noise. And in order to achieve the capacity, you are sending a signal XFL, which is Gaussian distributed, and have an energy per symbol Q, which can be computed as taking full power P in watt and divide by the bandwidth B, because that is the number of complex symbols per second. And we denote the power spectral density of the noise N0, and this is also something that's complex Gaussian. Then the channel capacity is computed as log 2 or 1 plus an SNR that you have at the receiver side, which is the transmit power Q multiplied with absolute value square of G divided by N0. And this is measured in bit per symbol. If you multiply with B in front, you get it in bits per second. And since this is a memoryless channel, we can drop this index L, because the structure is always the same for every L. And that is what we'll do from now on. When you have a transmitter and a receiver at a fixed location, well then G is given to you. So how can we improve the capacity? Well, we would like to improve the SNR, and what we can do is to use multiple antennas for that. And that is the main topic of this lecture. First, we will start with having multiple receive antennas, and then we will look at having multiple transmit antennas. So say that we equip the receiver with multiple antennas, and then we have antenna 1 here, 2, 3, and so on down to M. So M is a total number of antennas. For each of these antennas, we are applying the same system model as before. So when we are sending a signal X here from a transmitter, To reach the first antenna, it's multiplied with the factor G1, which is the channel response to this antenna. We are adding noise N1, and then we get Y1. And it's the same thing for Y2. The same transmitted signal is multiplied with another channel response, G2. We get another independent noise term, and we get Y2. So all of these noise terms have the same power spectral density as before, and they are assumed to be independent because the noise is thermal noise appearing in the receiver hardware. And we can continue modeling all the antennas in the same way here at the receiver side. And we can also put them in a vector form like this. So we take the M received signals in one vector. For each one of them, we take the transmitted signal, which is the same one, but we multiply them with different channel responses. So we put them in this vector here. And then we add a vector with the noise here, N1, N2, down to Nm. So this is our received signal vector. And we have a vector describing the channel. And we have a vector describing the noise. And we can write this in short form and use the boldface to denote vectors. All of them have the same length m here, so y, g, and n are vectors, but x, the signal here, is not a vector, it's a scalar because it's transmitted from one antenna here. So let us look at this received signal. What can the receiver know about its structure? Well, since y is a multiplication of the transmitted signal times the channel vector g plus noise, well, if the channel vector g is this one in the vector space, then x times g is a vector that is parallel to g, but it could be longer or shorter, and since we are considering the complex domain, we can also rotate the faces, but here we're neglecting that and only look at a two-dimensional illustration where we are considering the first and the second antenna. So that is g times x. Then to that we are adding the noise n, which is a vector. The noise vector can point in just any direction, and it actually is uniformly distributed over all directions because the elements are independently distributed and have the same distribution. So if we reorder the element, we can change the distribution. So that means that it needs to be uniformly distributed over all directions. The important thing now is that we are taking the noise, we are taking the received signal g times x, and we add them together, and then we get y, which is something that is pointing in this direction. And what can the receiver do now? Well, the receiver would like to figure out what is x. Since x is a scalar and y is a vector, we would like to turn y into an estimate of x. So somehow we should take this vector and project it to a scalar number. If the receiver knows g, it also knows that the signal is only living in that dimension that is pointed out by the vector g. And all the noise realization that are pointing in orthogonal directions from g can be ignored. So only the part of y that is parallel to g can contain the desired signal, and all other dimensions, which will be m-1 dimension if you have m antennas, they will only contain noise. So what we should do is that we should take y and project it onto g. And this is known as maximum ratio combining. So what we are doing is that we take y, we project it down to something that is pointing in the same direction as g, and an orthogonal projection of y onto g is obtained by taking y, compute an inner product with g, and then we should normalize it as well so that the length of g is not impacting it. Then the absolute value of this will be the length of this projected version of y. And remember, y was g times x plus n, so if we are taking inner product with g divided by its norm, so this is sort of the direction of g, well then we get this factor and we get this factor. The first factor is a scalar. Since the numerator here is containing the inner product between g and itself, that is equal to the squared norm of g. We are dividing with the norm of g as well, so this scalar here is actually equal to the norm of g. This is a noise term, and the projection is taking out the noise in one dimension, the dimension that is aligned with g. And there the noise power spectral density will still be a naught. This operation that we're doing here is called applying a combining vector. And we notice that we now have a SISO channel because this is a scalar. This is scalar multiplied with our transmitted signal, and this is a scalar noise. So this is precisely as the SISO channel that we had before. It's just that what we called g before, the channel response, have now, after our received combining vector was applied to the received signal, turned into the norm of the channel vector g. So the channel capacity should be obtained by taking our transmit power, Q, divide with the noise power spectral density N0, and then we should take the channel response G and square it, and in this case the channel response became the norm of G, so we get the squared norm of G. So that is the SNR that we get in our capacity expression, and log 201 plus that is the capacity in bits per symbol. So to achieve the capacity of the timer channel, we are sending a signal X, which is still Gaussian distributed and have Q as its energy per symbol, and the receiver takes the received signal, project it onto G using this combining vector, which we call maximum ratio combining, because it's maximizing this signal to noise ratio. And what is happening then is that you take your M antenna, all of them gets one copy of the transmitted signal and one copy with independent noise. You add the signal copies together in a coherent manner using maximum ratio combining, while the noise is averaging out over the M antennas, and we get the same noise power spectral density of the effective noise here and not. Let us now move on and consider the opposite scenario, a multiple input single output channel. So we have the same device as before with M antennas, but now we're transmitting in the opposite direction. And the signal we're transmitting from our M antennas is called X1, X2 down to XM. Each one of them is propagating over the same channel as before, so X1 is multiplied with G1, X2 is multiplied with G2, XM is multiplied with GM. We add them up over there, we add noise, that is independently distributed with N0 as its power spectral density, and we get Y as the received signal. We can represent this whole thing also in vector form. So Y, which is a received scalar, is a product between a column matrix with X1 to XM and a row matrix with G1 to GM. And if you multiply these two together, you get X1 times G1 and XM times GM, and we add all those things up and we add noise to it. And remember, G1 to GM, we had a vector before that was called like that. That was the channel vector. But now it is a row matrix instead of a column matrix. So we have taken the transpose of that vector. And if we call X1 to XM as the boldface X here, then we have this inner product here and we add noise to it. The noise is just a scalar number because we have only one receive antenna and noise is created in the receiver hardware. What we should do is to select the way of transmitting from our M antennas. And this inner product here is making sure that even if we are transmitting an m-dimensional signal represented by an m-dimensional vector, the receiver can only observe one dimension because it has one antenna. And therefore, we apply something known as precoding or beamforming, where we let x be equal to w, which is a unit norm precoding vector, which points out one direction in our vector space. This vector is fixed and we will optimize it later, but we multiply it with an information signal, which is complex Gaussian and have this energy per symbol Q as before. This is a scalar and the receiver can receive a scalar, so that makes good sense together. So x is equal to w times x tilde, and we put it in here. And what you should notice here is that this is an inner product. However, it is not an inner product between x and g, because inner products contains the conjugate transpose here. Since there is no conjugate, this is actually an inner product between x and g conjugate, because the inner product will then take out this conjugation. When we are using precoding like this inner product even becomes something between g conjugate and w. And what that means geometrically is that we are transmitting something in a vector direction, w. It's not in our three-dimensional world, it is in the m-dimensional world where our transmitted signal lies. It's a vector space. And the channel is then projecting whatever we are transmitting onto G conjugate. So if we are transmitting something in direction W, then if we are projecting G conjugate onto W, we get something with the length that is given by the inner product between G conjugate and W, like this, and we take its absolute value. That is the length here. And if these two are pointing in different directions, then this length is shorter than W. And this is represented by this missing piece here, which is longer than what we get after the projection. So if we are transmitting something in a direction that is not fully aligned with G conjugate, well then that extra energy that is pointing in the wrong direction will just vanish over there. It will never reach the receiver. So for that reason, the best precoding is maximum ratio transmission, defined like this. W should point in the same direction as G conjugate, and since it needs to be a unit norm or unit length vector, we are dividing with the norm of G. We could also write this as the norm of G conjugate, but that is the same thing, so that's where we omitted the conjugate in that term. So the received signal Y is G transpose multiplied with the precoding vector W, and we have now been applying maximum ratio transmission, and then we have our data signal G tilde, and then we add noise. And this here is an inner product between G conjugate and itself, so it's equal to the squared norm of G conjugate or the squared norm of G. We divide with the norm of G, and we get just the norm of G. Multiply with X tilde plus noise. And once again, this looks exactly as a SISO channel, where we have a channel response that is equal to the norm of G. So the capacity will once again be given by the formula from the SISO case. Log 201 plus an SNR, where we have the Q and N naught, and then we take the scalar factor here in front of the signal, which is the norm of G, and we square it. So the capacity of the MISO channel is like this. And we are achieving it by taking our signal and precode it or beamform it in a direction that matches precisely with the direction of the channel. And when I say direction, I'm not referring to directions in our three-dimensional world. I'm talking about directions in the m-dimensional world where the vectors here are living. This capacity expression is something that we already have seen, because we now have the same capacity expression in both the SIMO and the MISO channel. And we achieve the capacity with some kind of beamforming along the channel vector. So when we are receiving, we apply receive combining all the signals over the antennas so that it matches with the channel vector G. And when we are transmitting, we apply precoding that is also aligned with the channel vector. And in general, both of these things are referred to as beamforming. Compared to a SISO channel, where here we will only have the magnitude squared of one channel coefficient, we get a beamforming gain because we have the squared norm of this channel vector G, which is the sum of m terms, each of them being the magnitude squared of a particular channel element. And since you're summing up m terms, compared to just one term in the SISO case, we typically have a beamforming gain that is proportional to number of antennas. So roughly speaking, we get m times more signal over a channel. The SNR is m times larger. The beamforming that achieves the capacity, the optimal beamforming, have been given different names over the years. Maximum ratio combining, or MRC, was what we are using in the reception, and maximum ratio transmission is what we were using in the transmission over the MISO channel. But some people are calling the transmission conjugate beamforming because we're taking G conjugate and align our beamforming with that. And at the receiver, it's sometimes called match filtering. And a key property of these methods is that antenna M contributes proportional to how good its channel is. So an antenna that have an absolute value square of GM that is twice as large as another antenna will contribute twice as much to the sync-to-noise ratio as that other antenna. Let's now switch focus and have a little bit look at the geometrical properties of transmitting. So this was a graph that I was showing you on the previous lecture, when we have multiple antennas at one point here and we would like to send the signal towards this receiver over here. In this case, we have 6 transmit antennas, and we can interpret the beamforming as sending a beam focused towards the receiver here. So we get a directivity in our radiation pattern, even if each of the individual antennas have an omnidirectional pattern. The beamforming gain means that we are sending more energy in the desired direction, and in this case we get m times stronger signal, and this is also known as an array gain or power gain. This illustration here is actually only a valid interpretation of the beamforming in line of sight channels. but that will be the focus of today's lecture. So now we will look at free space line of sight communication, where there is a direct path from the transmitter to our M receive antennas, and there are no other paths. The distance to the first antenna is denoted D1, the distance to the mth antenna is denoted DM. And the goal now will be to derive a channel model, how the G vector will look like in this particular case. We do it for the SIMO channel, but we can apply the result for the MISO channel as well. To compute the channel vector, we need to go back to continuous time and go through the steps that are needed in order to develop the discrete memoryless channel. And there is a background video where these details are considered. Now we will only go through the most essential thing. So we have a transmitter sending a signal to a receiver, and there is a distance dm between them. So this is the mth antenna. The impulse response in the passband will then be that the signal gets delayed because it is propagating over there. So we have a delta function that is saying that we have a certain delay, tau m. And this is the propagation delay, tau m is equal to the distance dm divided by c, which is the speed of light. Moreover, we assume that the transmitter and the receiver is equipped with isotropic antennas. In this case, we know what the path loss is going to be. And now we take the square root of that one and call it the amplitude loss and multiply the delta function with that one. It's lambda divided by 4 pi times dm, this distance here again. And then I'm adding an additional factor here. I call it the synchronization parameter because it's used at the receiver to tune its clock so that it compensates for the average propagation delay. And we will see exactly how to do that in a moment. When we have this impulse response in the passband, then we achieve an equivalent impulse response in the complex baseband by taking the same thing and just multiply with e to the power minus j2 pi fct, where fc is the carrier frequency. So we are essentially taking this impulse response in that passband and we move it down to the complex baseband. Apart from that, it's the same factors that are appearing. And then when developing a complex baseband model by sampling things, using pulse amplitude modulation, all of the properties that are needed in order to reach that point, the symbol sample systems after our sampling is that at the mth antenna, at time index L, we receive a summation over the symbols that we are transmitting at different sample time indices. Then we have the amplitude loss here, and then we have e to the power minus j2 pi fc, and the t is replaced with the delay that we have in our delta function here. And tau m was dm divided by c, and we get the minus the eta here, which was the synchronization parameter. And in pulse amplitude modulation, we are using a sync pulse. We get L minus k, that is the shift of the sync function, and then we get this additional factor that is due to this time delay here as well. And it is multiplied with b, the symbol time. The sync function is the pulse we are using in our pulse amplitude modulation so that we can send one x after the other and distinguish between them at the receiver. So the sync function has this property that the sync of 0 is equal to 1 and the sync of any other integer is equal to 0. When L and K are different, we have another integer here. So it should be 0, apart from that we have this additional shift here. But since the synchronization parameter is something that we can select eta to be equal to dm divided by c. That is what synchronization means. And in that case, this term goes away when L and K are different, which means that the summation over xk becomes just xl when k is equal to L. Alpha m remains. This term here becomes e to the power of 0 because dm divided by c is equal to eta. And the sync function is 1, and we have only our noise. So then we have developed a memoryless channel model for this case. But that is when we have one antenna. When we have multiple antennas, which is the case here, then we would like to use the same sampling time on all our receive antennas. So this is the received signal from the previous slide for antenna M. And since the distance dm is typically different for every antenna, we cannot select eta to be precisely equal to dm divided by c for every antenna. We can only do it for one antenna. However, if the differences in the distances are fairly small, we can still find one eta that is close enough to all of the dm terms so that b times eta minus dm divided by c is something that is negligible compared to L minus k. and that is called a narrowband assumption. Namely that B times dm divided by c is roughly the same for all the antennas. We will make the narrowband assumption in the rest of this lecture, and we will also assume that we are using antenna 1 as a reference antenna. So we select eta to match with its delay, d1 divided by c. And I will also replace now c divided by fc with lambda, because that is the wavelength and the definition of the wavelength. In that case, we can replace eta with d1 divided by c everywhere, and we can then replace fc divided by c with 1 over lambda, and we get lambda here. Next, we use the narrowband assumption or approximation to neglect all the terms here where k and l are different. Then we get x of l, we get alpha m, and we get this term e to the power minus j2 pi dm minus d1 divided by lambda. So that is the difference in distance to the first antenna and to the mth antenna. And then we have our additive noise. So now we have developed a channel model for the line of sight case. We have for every antenna here alpha 1, alpha 2 down to alpha capital M, and we also multiply each term with e to the power minus j2 pi, and we have the difference between the distance to that antenna and to the first antenna divided with the wavelength lambda. We can simplify this channel model even further by considering a standard form of array, a uniform linear array. These are antennas, m of them, that are located along a line, having the same spacing, delta, between them. And for this array, we can define at the first reference antenna here an angle, phi, which is defining sort of the directivity of the array in general. So when the angle is 0, we have what is called the broadside direction. So signals coming from that direction are coming in from a direction orthogonal to the direction of the array here. When it's pi over 2 or minus pi over 2, well, then we have the end phi direction. Then the signal is coming in from the same direction as where the array is located. For this type of array, we can still define the distance d1 and dm to the different antennas here, but we would like to figure out what happens to signals that are reaching to these different antennas. What is the relationship between d1 and dm when the signals are coming from a particular angle? And to figure that out, we need to talk a little bit about the near field and far field. And we start with talking about an antenna. When an antenna is transmitting a signal, I've said repeatedly that the signal is expanding as a sphere. That means that a waveform that is impinging on a receive antenna that is flat will not be matched perfectly with the signal wavefront, which is curved, because it's a spherical wavefront. So suppose the length here is a of the receive antenna. Then you have one distance d to the center of it, but you have another distance d prime to the edge of it, both the upper and the lower one. We can compute the length difference, d prime minus d, that is the extra distance up here that the wave needs to propagate to reach the corner compared to the center. And from the Pythagorean relationship, we know that we should have this longer side here, which is d squared, multiply with half of a is the total length here, squared, and then we take the square root of that is d prime, and we subtract d from that. This expression doesn't help us very much to understand it, but if we are applying a first order Taylor expansion of this, then we can simplify it further and get a squared divided by 8d. So that is the extra distance up here. And when considering what is going to happen as the wave is propagating over that extra distance, actually the wavelength is important, because that tells us how many times per second that the wave is oscillating up and down. And suppose that we can live with a small phase difference between the corner and the edge. We can never get rid of it perfectly, but a typical rule of thumb is that we can live with a pi over 8 phase difference, which is represented like this between the blue and the red curve. That is like 22.5 degrees of phase difference. To compute the phase shift, we take the length difference, multiply with 2 pi divided by the wavelength lambda, and we want it to be smaller or equal to pi over 8. If we take this equation and solve for d, we will get d should be greater or equal to 2 times a squared divided by lambda. So this is the distance that we would like the receive antenna to be at in order for us to be able to neglect the phase difference between the center and the edges. And this has been known as the Fraunhofer distance. Since the length of an antenna typically is at the order of the wavelength, if you put in a wavelength here, you will get 2 times the wavelength because you have a wavelength twice here that is cancelling out. So that means that it's only over a wavelength for a few wavelengths that the near field is appearing when you're talking about an antenna. So we can typically neglect the near field effects, and that is good because there are other types of electromagnetic properties that are appearing in a near field, like evanescent waves and magnetic induction effects like that we can totally neglect. So we can forget about that, but the Fraunhofer distance is interesting in another way. We can namely define the near field and the far field of an entire array depending on if the waves that are propagating and reaching the array will look like they are curved or not when they are reaching the array. So the individual antennas having a length A here is typically in the far field of the transmit antenna, but the entire array might not be. If we are applying the same type of thing, we say that we are in the far field of an antenna if the distance to the antenna is larger than 2a squared divided by lambda, and that we typically are. But if you have a length b of an array, then you put it into the same formula to see if there will be a big phase difference between the antenna here in the center and the one at the edge. Well, then you get this formula here with b squared instead of a. If we put in some numbers, 3 GHz band, wavelength that is then 1 decimeter, and you say that your array is 10 wavelength long, so 1 meter long, which typically is as long as arrays are today, then this becomes 20 meters. So in mobile communications, we are typically in the far field also of the arrays. So we will use this far field approximations so that we can neglect the curved waveforms from now on. When the receiver is in the far field of the transmitter, then the spherical wavefronts that are emitted will look almost like planar wavefronts. And that means that the angle of arrival will be the same for all the antennas approximately. Suppose here the angle of arrival is theta, then we can see that the wavefront is reaching the first antenna first, then the second one, and then the nth one, and there is some additional distance that it needs to move. And we don't need to care about the curvature, only the additional distance here, and that will lead to a phase shift. So if you have D1 to the first antenna, then from the trigonometric rules here, you can say that, okay, this angle here of arrival is also showing up here, and then this extra side here will be the length from 1 to m. So it's m minus 1 times the antenna spacing delta, and then you multiply with the sine of the phi angle, and that gives you this extra distance here. So dm is equal to d1 plus this extra distance. So what impact does it have on our channel model? Well, when it comes to the attenuation over the channel, or the channel gain, then the distances are approximately the same, because it's only the total distance from the transmitter to the receiver that matters. So if we are computing the channel gain like this, then dm is approximately the same. We can replace it with d1 or d, and there is a common channel gain for all of the antennas. However, when we are computing the phase shifts in the channel vector, it is not the absolute distances to the receiver antennas from transmitter that matters, but difference between them to different antennas. So we get dm minus d1, and that extra distance is m minus 1 times the antenna spacing delta times the sine of the angle of arrival. So we get this expression over here, and that is divided by the wavelength. And if the angle of arrival is 0, so the signal is coming in from this direction, then we get exactly the same value here, sine of 0 is 0, while if the signal is coming in from widely different angles, then it will reach some antennas first and then other antennas. And in terms of the channel gain, it doesn't make any difference, but in terms of the phase shift, it does. So to summarize, when we are computing the channel vector for a uniform linear array, or ULA, then if we have m antennas in our receiver, we have an angle of arrival, phi, we have a wavelength lambda, we have a distance delta between the antennas, the neighboring ones, and the distance is d to the first antenna. Then a channel vector is computed like this. We have the channel attenuation in front, lambda divided by 4 pi d. And then in addition to this channel attenuation, you have different phase shift on different antennas. there is no phase on the first antenna because we're using it as the reference antenna. But then with respect to that antenna, there are additional phase shifts. Delta times sine of the angle of arrival. And then we multiply that with how many antennas away we are. And this model was derived for the SIMO channel, but you can also utilize it when analyzing the MISO channel case, because we are just flipping the order of a transmitter and the receiver. And the whole concept about near field and far field and Fraunhofer distances are applying in that case as well. So remember, this is the channel model for a uniform linear array in free space propagation, and under the assumption that the total distance d here is larger than the Fraunhofer distance applied for the entire array. And even if that sounds like a large number of assumptions, it is actually something that is realistic to consider in line-of-sight scenarios in reality. So recall that the channel capacity had this formula both for the SIMO and the MISO channel case, and now we have a way of computing the channel vector g in the line-of-sight case. Each element had the same magnitude, but different phase shift. But when we are computing the square norm, the phase shifts are disappearing. So we get m, which is a number of elements, and then we get the squared magnitude of each of the elements, which is then this free space propagation loss. So the channel capacity expression is simplifying to log 2 of 1 plus q times beta times m divided by n naught. So we see that the SNR grows linearly with the number of antennas. So that is the beamforming gain that is very clearly seen. One way of illustrating beamforming from a transmitter is that you take one antenna that is radiating its power in an isotropic manner. Then you take two antennas that are transmitting the same signal but with half of the power, and they are creating a directive transmission like this with twice the amount of power in the main direction, forward in this case. And then you can continue by taking four antennas that are sending the same signal, and then you get the 4 times stronger signal in the main direction. And the shape here is what we call a beam, and we have the same total power in all of the 3 cases here. This example is showing how you form a beam in the phi angle 0, but by varying the phi angle and computing the corresponding phase shift for different antennas, you can direct your beam in other directions. This is the typical way of illustrating beamforming, but the question is this an accurate illustration? Well, in a moment I will show you that it is an accurate illustration, however it's only an accurate illustration in line-of-sight scenarios. A beam, or whatever we would like to call it, looks very differently in a non-line-of-sight scenario. Then the emitted signal might not have any clear directivity. It might send beam in a number of different directions, and the important thing is that there are many paths leading to the receiver, and we are making sure that the emitted waveform is moving over all these paths and are reaching the receiver in phase so that you are utilizing the propagation environment in the best possible manner. And we will consider more how to model such scenarios in the next lecture. So, talking about the first question, when you are beamforming in a particular direction in a line-of-sight scenario, you can expect that receivers located at that angle will get the beamforming gain. But if the receiver is located in a slightly different angle, it will probably also see an amplification, and that is quantified by the beamwidth. So suppose we are beamforming in the direction phi beam, and then we are moving around the receiver in another direction, phi. We can then use the channel model that we have computed so far to compute the beamforming vector, which is this vector here, and then we can compute the channel vector to another direction. And here we have omitted the attenuation, so it's only the inner product between the beamforming vector and the channel vector to the location of the receiver. We take the absolute value square of this inner product, and we divide by m because we need to normalize the beamforming vector to have length 1. We can now compute this inner product for any value of the angle phi. So let us change it from minus pi over 2 to plus pi over 2. And we are here omitting the pi. So here we are showing the angle from minus 1 over 2 to plus 1 over 2 in multiples of pi. In this example, we have 10 antennas at transmitter, we have half a wavelength spacing, and we are beamforming in the angular direction 0. And that's what we see here, that if the receiver is in that particular direction, we get the beamform gain of 10, which is matching with the number of antennas that we're having. Then if the receiver have a similar angle, it will also see a beamforming gain that is above 0 decibels, which means that it's stronger received signal there as compared to having an isotropic transmit antenna. The shape here is called the main beam, and we see that there is a certain starting point. It goes up to the maximum gain and then it goes down again, and there's a symmetry here. In addition, there are some additional beams or lobes that are called. So all of these things are called main beam or main lobe and side beam or side lobes. So these side lobes are representing the leakage of interference in other directions, and that is unavoidable even if we are focusing the energy in one particular direction. If we would like to figure out how wide this beam is here, well then we can of course look in the graph here and measure what the width is. But we can also quantify it, and we can quantify it in different ways. One way of measuring it is the amplification beamwidth, in which interval is the amplification larger than 0 dB. That is when we are benefiting from the beamforming. Another way of defining it is to look at the half power beamwidth. This is representing the interval width here, from having the maximum gain and going down 3 decibels, representing having half of the beamforming gain. So from m to m/2. These two definitions are probably the most useful one in order to talk about the beamforming and its width, but it's easier to compute mathematically what is known as the first null beamwidth. That is to compute from this starting point to this starting point. So there are some angular directions where there is no signal energy at all being observable. And one can compute mathematically that the width here is 4 divided with the number of antennas in radians. So that tells us that the more antennas we have, the narrower the beam is. Here's an example of that. We are starting from the 10 antennas that we had in the previous slide, and then we are changing in the red case here to 20 antennas. We can see that we get twice the beamforming gain, which is represented here by 3 decibel increase. And if we are comparing the first null beam width, it's approximately half of what we had in the blue case. So the main principle is that the more antennas we have, the stronger the main beam becomes, the more narrow it becomes as well, so there is less leakage in other directions. But there will always be these kind of ripples, side lobes in other directions. There's always some leakage, but the main beam becomes more and more like a laser the more antennas we're having. In this lecture, we considered having multiple antennas at the transmitter or at the receiver. And we saw that when you have such a setup, if you're transmitting in one direction or in the other direction using the same total power, well, you have the same channel capacity. And you achieve it using maximum ratio combining if you have multiple receive antennas, and maximum ratio transmission if you have multiple transmit antennas. Then we were looking into the capacity when you have a line of sight channel, so we characterized the channel itself. We saw that all antennas are contributing equally to the capacity, and it's phase shifts that is different for the different antennas, and we can relate that to the geometry from which angle that the signal is coming or where it's going to be transmitted. We are achieving a beamforming gain of m, where m is number of antennas, so it's precisely that in line of sight channels. And the beam width, the width of the signal that we are transmitting, becomes inversely proportional in the angular domain with the number of antennas.